Hello students and welcome to a new lecture. We are going to be discussing electron configuration, which is the distribution of electrons among the atomic orbitals. We have learned about the presence of atomic orbitals, and atomic orbitals will be occupied by electrons. So how do electrons distribute themselves in these orbitals? We are going to be describing every orbital and how many electrons are located within that orbital by saying, for example, 1s1. So what does that mean? 1 is the principal quantum number. S is the angular quantum number L, which is the orbital that is occupied. And 1 is number of electrons present in that 1s orbital. This is what we call the electron configuration. However, we can also represent the exact same information using what we call orbital diagram. In an orbital diagram, we show the orbital by drawing a box and we name the orbital right underneath the box. So if you look at this box, this is the 1s orbital and I have to mention the name underneath it. And then one arrow means an electron. So inside this orbital, there is one electron, meaning 1s1 is electron configuration, and this is electron diagram. They have the exact same information, but this is what I call electron configuration, and this is what I call orbital diagram. And why am I making this distinguish? Because you need to know what the question is asking you. Is the question asking you to show electron configuration, or the question is asking you to show orbital diagram? Here are the orbitals, and their energy, as you can see, are dependent on both the N and the L value. Let's look at that. The lowest orbital energy is the 1s orbital. N for this equals 1 and L equals 0. If you add 1 plus 0, that's equal 1. Now let's look at 2s. N equals 2, L equals 0, 2 plus 0 equals 2. So this is why this is higher energy than 1s, because again I'm saying that the energy depends on both N and L. Let's go to 2p. N equals 2, L equals 1. So 2 plus 1 equals 3. So 3 is higher than 2. That's why 2p is higher in energy than 2s. Let's look at 3s. N equals 3, L equals 0. 3 plus 0 equals 3. So some of you might ask, well, if both of these 3s and 2p equal 3, why is 2p is lower level than 3s? If they have the same number, when you add n and l value, then and they are having two different quantum numbers, then the one with the lower quantum number has lower energy because it's closer to the nucleus. Now 3p, n equals 3, l equals 1, that is 3 plus 1 equals 4. Now same thing here, 4s, n equals 4, l equals 0 equals 4. However, 3 is a lower quantum number than 4, therefore it is closer to the nucleus and lower in energy. Now, there is a reason why 4s is lower in energy than 3d. Let's look at that. N equals 3, L equals 2, 3 plus 2 equals 5. That's why 3d is higher in energy than 4s, and so on. Each electron has a unique wave function, and that leads us to a Powly exclusion principle. The principle states no two electrons in an atom can have the same 4 quantum numbers, because even if they were in the exact same orbital And if they were in the exact same orbital, it means that they have the same N, the same L, the same ML. But they're going to have different MS, which is the spin, because one of them will be spinning clockwise, the other one will be spinning counterclockwise, which means one of them will be assigned plus 1/2, the other one will be assigned negative 1/2. So here is an example. These two electrons are in 1s orbitals, right? So if I take this electron here and I want to state the 4 quantum numbers, and the 4 quantum numbers, remember, N, L, ML, and MS. N equals 1. L for S is 0. ML for S is also 0. MS, it has to be either going clockwise or counterclockwise, and therefore I have to assign randomly one of them, so it will be plus 1/2. Now, let's look at the other electron. What if I am stating the quantum number, the 4 quantum numbers for the other electrons? It is N for 1s is 1, L for 1s is 0, ML for 1s is also 0. However, it's the opposite spin, so it will be negative 1/2. That's why no two electrons in any atom have the same 4 quantum numbers, because the closest they can possibly be to each other is to occupy the exact same orbital. And even when they do, they still have to differ in the MS. Now, if they are in different orbitals, they will differ in, can be N or L or ML and so on. Each subshell has a maximum number of electrons based on that. So because S is one orbital and I can only have 2, so S can take 2 electrons. There are 3 P's and each one can take 2 electrons, so the total will be 6. There are 5 D's, each can take 2 electrons. Again, the total is 10. 7 F's, and each can take 2 electrons again, therefore a total of 14 electrons. Then we can look at what we call Aufbau Principle. And in Aufbau Principle, we are talking about that electrons occupy the next available orbital with the lowest energy. So what does that mean to me really? What it means is you fill lowest energy first. Just remember this simple statement. We fill lowest energy first. Let's look at that. Hydrogen has 1 electron. So when I'm going to put that electron, I have to put it on 1s. I cannot put it on 2s because I fill lower energy first. Okay? Now, if I go to helium, which is 1s2, then helium will have the second electron here. I cannot put the second electron somewhere else because I have to fill lowest energy first. If I go to lithium, 1s2, 2s1, then the next electron, I finished 1s, I can't put any more, so 1, 2, and then the third one will be here. And that will continue, right? So after lithium, you have beryllium, you're gonna go here. Then after that, we're going to have boron, and we're gonna have to keep continuing with our elements. So you're gonna have like carbon, then you're gonna have nitrogen. And if you see what I'm doing here, which we will talk about in the next principle, which is I parallel electrons before I pair them, right? If you have multiple seats available, even if those seats are arranged in pairs, like let's say you climb into a bus and on both sides there are pairs of seats available, all of them are empty, which means all of them are available and they are all equal energy. They're all gonna take you to the exact same destination. And there is one person sitting on one of the seats. Chances are you are not going to pair yourself next to the person. You're going to occupy if because they are all similar energy, you're going to go and sit on the pairs that are empty and available, which we will look at this principle in the next slide together. The orbitals that have same energy, we call them degenerate orbitals, meaning you have p orbitals has a 3, the px, the py, and the pz. They are all same energy, so we call them degenerate orbitals. D has 5 of them, so I'm going to call those two degenerate orbitals. That is the principle that I am talking about. Hund's rule. Electrons do not pair up unless all orbitals in the same subshell already contain one electron. Meaning, if you remember how I was filling electrons, 1, 2, 3, 4, 5. Now the 6th electron cannot go and pair itself here. This is wrong. Okay? What should happen is this. So 1, 2, 3, 4, 5, 6, 7. 8 has to be paired, no other option, because I cannot jump to 3s, it's higher in energy. We fill lower energy first. So 8, 9, and 10. Now 11th electron going to be here. 12th electron here. And then you have 13, 14, 15, 16, 17, 18, and so on. Again, one more time, we are going to try to put an emphasis on the fact that the orbitals with the same energy are called degenerate orbitals. We're going to use the periodic table to determine the electron configuration. Every row is considered to be equivalent to an energy level. Length of the row depends on the types of the subshells. Let's look at that. Look at periodic table, right? You will see that group 1a along with the group 2a represents the s orbital. And I want you to look at that carefully with me. Now this is helium. Electronically, helium should be here. That's why it's purple. However, the reason why we send it there because it is a noble gas and we want it to be with the noble gas group. But electronically, it is electronically next to 1s. So look what we do. We fill first 1s, hydrogen, helium. Then we fill 2s, lithium, beryllium. Then we fill 2p. Then we fill 3s. Then we fill 3p. Then 4s. Then 3d. Then 4p. Then 5s. So you never have to remember the energy levels. Remember how we have 1s, 2s, 2p, 3s, 3p, and so on. You never have to remember that because if you look at the periodic table, it's already stated there. You can see the S block elements, the P block elements, the D block elements, and the F block elements, right? You fill again 1s, 2s, 2p, and as I go in the arrow, the atomic number grows, which means the electron numbers do grow as well. So again, one more time to see the periodic table representing the blocks. 2s, I can place 2 electrons. In 6p, I can place, in p orbitals, I can place 6 electrons. In the d orbitals, I can place the 10 electrons. And in the f orbitals, I can place the 14 electrons. So let's go one more time here. And I want you to notice this. So let's look at the p orbital. Look how many electrons I can put here. 1, 2, 3, 4, 5, and 6. And why is that? Because p orbital has 3 different orientations. Each one can take 2 electrons, right? So the number of, because when I go this way, I increase numbers of electron because I'm increasing the number of the atomic numbers, right? The number of protons. Now here, in the d orbitals, I can place 10 electron. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And so on. Okay. We also can use what we call the noble gas as the core when we write the electron configuration, right? So assume we want to write the electron configuration of arsenic, right? There are so many electrons to fill, and it will be very, very long to write 1s2, 2s2, 2p6, 3s2, 3p6, and till all the way till we get to 4p3, which is where the last electron in arsenic is located. So I'm going to show you both examples, right? If I am writing what we call the full electron configuration, so pay attention to the question if it's asking for the full, then the full electron configuration for arsenic, and we put them between brackets, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3, right? This is pretty long electron configuration. This is also equal to using what we call the noble gas abbreviation. So this is arsenic. We look at the last noble gas that came before arsenic. In this case, it will be argon. And another way to write the electron configuration of arsenic will be the electron configuration of argon followed by 4s2, 3d10, 4p3. These two are equal, right? Because if you want to really think about it, guys, all the way to here, that is the argon electron configuration, which is this one here. Then after that, it's 4s2, 3d10, 4p3. It makes it shorter and sweeter and, less confusing also to write. Another thing we want to learn about the electron configuration and the effect on the atom properties, that if you find electrons in any electron configuration, if you find any electron, it can be one or more, but one is enough, that is unpaired, standing all by itself, that makes the atom to be paramagnetic. And what does that mean? It means that this atom will react to an magnetic field. However, if all electrons in the element, all of them, are paired, that will make the atom to be diamagnetic, which means the atom will not react to a magnetic field. Here is an example. In this atom, it turned out when we did the electron configuration that there are two electrons that weren't paired. As I said, even the presence of one electron that is not paired will cause the atom to be paramagnetic. However, if all electrons in the atom is paired, then that atom will be diamagnetic. Please pay attention to the following advice or hint. If you want to know how to determine, because that can be a question, I can ask you which of the following atoms is paramagnetic. If you do electron configuration, it's very hard for you to see. However, if you do orbital diagrams, because in orbital diagrams you're going to have to make a square for every electron and you will see who's paired and who's not, you will be able to see if there are paired electrons or if some of them are unpaired. So one more time, the advice is don't do electron configuration to answer the question, draw orbital diagrams. That's also going to lead us to the definition of valence electrons. We will talk a lot about valence electrons in the future when we are covering bonding, but valence electrons by definition are electrons in the outermost principal shell, or the largest N. So let's look at that. They determine the chemical properties. So for example, if I can claim that sulfur and oxygen do have similar way to react, which is chemical property, it is because they both have the same number of valence electrons. What does that mean? In their highest N, they have the exact same number of electrons. Here is an example. This is the electron configuration of silicon. 1s2, 2s2, 2p6, 3s2, 3p2. The highest N for silicon is 3. How many electrons are there at that level? Well, there is a 3s with 2 electrons and 3p with 2 electrons. So there are total of 4 electrons. So number of valence electrons for silicon will be 4. Okay, let's look at another one. For germanium, the electron configuration goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. One more time. They still have 4 valence electrons. Why? Because at the highest N, and the highest N here is 4, there are total of 4 electrons. The 2 here and the 2 here. Okay? So this is here. If I tell you, draw the electron configuration of the valence electrons of silicon, it means you're only going to say this. Okay, so you want to pay attention to every word in a question. If I said, draw the electron configuration of the valence electrons here, you're only going to have this and this because these are the valence electrons. Now, writing electron configuration with periodic table. Silicon, we just saw that the way we write the electron configuration for silicon will be 4s2. I jumped ahead of myself. 1s2, 2s2, 2p6, 3s2, 3p2. Because silicon, guys, has 14 electrons, right? So when you look at silicon, you know there are 14 electrons. Then you start to fill the orbitals, starting with the lowest energy first. So 2 in the 1s, 2 in the 2s, 6 in the 2p, and so on. Now we're going to work on these examples together. So you have to look at a periodic table. Tellurium has 52 electrons, so that's a lot of electrons. I'm going to use the noble gas configuration. The last noble gas before tellurium is krypton, so I'm going to write here krypton. And then after that, I have 10 electrons in 4d10. Actually, I'm going to gonna write it exactly the way it appears in the periodic table. That's how I would like for you to guys write it. It will be 5s2 4d10. Please look at the periodic table as we are doing this work together. And then 5p4. Okay, now again with the periodic table in front of you, let's look at lead. Lead has 82 electrons, so I'm gonna again use the last noble gas before lead. In this case it will be xenon. Okay, now if you are following in the periodic table and you're following by the atomic number where the electrons are, you will find that after xenon, please take note of this. After xenon, it's when I'm going to start the f orbital to fill in the f orbital. Look at the atomic number of the elements and see how they, after 6s2, the electrons goes to 4f. And I place 14 electrons before I fill 5d10, followed by 6p2 for lead. So this is what we are trying to tell you here. For F block elements, assume that F subshell is filled before the D subshell. Last one here is an anion. This is oxygen, okay? Now oxygen, the normal configuration of oxygen is the following: 1s2, 2s2, and 2p4. Okay, that is neutral. That is a neutral oxygen. However, when I want to have an anion, it means I added, right? I'm going to, I am adding 2 electrons to the neutral oxygen. Right? So neutral oxygen has how many electrons again? It does have 8 electrons. Here they are. But oxide will have 10 electrons. So what does that mean? It means now instead of me filling 8 electrons, I'm going to be filling 10 electrons. So my configuration will be 1s2, 2s2, 2p6, which also can be written as the electron configuration of neon, because that is what we call the electron configuration of neon. Now, let's answer this question together. What are the possible quantum numbers for the last outermost electron in chlorine? Let's look at what does that mean to me. First, chlorine has 17 electrons. The way they are distributed in orbitals, it's neon, because 10 are in neon, right? And then 3s2, 3p5. So what are the possible quantum numbers for the last outermost electron in a chlorine? The last electron in a chlorine occupied, which is 1, 2, 3, 4, and 5. So if I pick this electron and I try to assign the 4 quantum numbers for this electron, what would they be? Well, it is in a 3p orbital. So remember, 4 quantum numbers: N, L, Ml, Ms. N equals, for that, 3. L for p orbital equals 1. Ml, it can be anyone between -1, 0, or 1. There is no rule which orbital takes what value, right? And since they are asking possible, it does have a possibility of -1 or 0 or 1. And when it comes to Ms, that electron can either be a +1/2 or a -1/2. These are the real possible 4 quantum numbers for the last electrons in the chlorine atom. Now, we do have 2 exceptions that we need to learn. Again, with the periodic table in front of you, we know that there are certain stability. So nature does not care about human equations and theory. Nature always have one motivation, which is to go to the most stable place. There is extra stability that comes from something we call half full or half subshell. And that means if I am to predict the electron configuration of chromium, the predicted configuration will be argon 4s2, 3d4. that is the predicted electron configuration based on us following the rules and following the electrons. However, that's what we predict. The actual one is argon 4s1 3d5. What happens here we call a promotion. One of these electrons in the 4s was promoted to occupy 3d. Why? Because having having the 5 electrons half filled the orbital bring extra stability to the atom. So the atom in the nature will do whatever is most stable. Now promotion costs energy, but the payoff of stability exceeds that cost, so that's what happened. Okay? Now how do you know to what elements you will be applying that? I'm going to give you my easy rule. Look at the periodic table. It's a chromium and all the elements underneath it. Chromium and all the elements underneath it. Now let's look at copper. If I am to predict the electron configuration of copper, it will be argon 4s2 3d9. However, the actual one is argon 4s1 3d10. Same story took place here. One of these electrons was promoted to 3d. It turned out that if I have this, which is full 3d, it provides extra stability of the atom. Again, that promotion does cost energy, but the stability outweigh that, so that's why nature chooses that. Now, how do you know what elements will also follow that exception? It's copper and all the elements underneath it. I call it the jewelry row, right? You have copper, you have silver, you have gold, the jewelries. Copper and all the elements underneath it in the periodic table. Now, last topic here is to show you how to do electron configuration of ions when these ions happen to be transition metals. So, we always lose or gain valence electrons to gain that noble gas configuration. So what does that mean? That all the movement always happens in the valence. So cations lose electrons, for example, like aluminum, and anions will gain electrons like nitrogen. And therefore, when we look at the electron configuration of the ions here, we will see that both the electron configuration of aluminum and aluminum cation and nitride anion are the same, and they are equal to the electron configuration of neon, because like nitrogen, guys, does have 7 electrons. So when it gains electrons, it will gain 3 electrons. When it gains 3 electrons, then the total electrons will be 10 electrons, which equals the electron configuration of neon. Aluminum has, as a neutral atom, 13 electrons, but it tends to lose 3. So 13 minus 3, so here you have 7 plus 3 for nitrogen. For aluminum, 13 minus 3, that gives you 10 electrons, which also equals the neon, right? So the electron configuration of the aluminum cation and nitride ion are isoelectronic with neon, equals to neon. Transition metals, it's when you remove the or form the cation and you have to remove electrons from S then D. Please pay attention to this rule. If you are looking at a transition element, you have to take electrons from S, because S is always higher than D when it comes to the n quantum number. We always take from the valence. And And they also can form multiple cations, so you want to pay attention how many electrons did they lose. So let's look at some examples together to make this point clear to you. The electron configuration of iron can be written as argon, four S2 3D6. So that is the electron configuration of a neutral iron. However, iron can be +2 cation, so which means it's going to lose 2 electrons. Now, make sure you don't make the mistake and take the last electrons you filled. The last electron you filled were in a 3D. When we lose electrons, though, we lose from the highest n, from the valence. We lose electrons from the highest n. So losing 2 electrons, you're going to lose these 2. So the new electron configuration will be argon 3D6. What if I am looking at iron +3? Then the electron configuration now, again, always have the neutral iron first. The first 2 electrons are coming from the 4s2. The third one is gonna come from the 3D. So it will be argon 3D5. Now let's look at copper and copper +1. Copper, as you guys just saw with me, it's an exception. And the electron configuration of copper is argon 4s1 3d10. Always have the neutral atom first. Even if I'm asking you about the ion of the transition metal, always have the neutral one first. Now, copper +1 means it lost 1 electron. It doesn't lose it from here. It loses it from the highest n. The highest n is 4. Therefore, the electron configuration will be argon 3d10. If it was copper +2, then it will be argon. I lose the 4s1 electron first, and then I take 3d9. Now remember that I will be putting the exceptions as questions. Make sure you know the exception, because remember how you only have 1 electron in the S and 10 electrons in the D when it comes to copper. I hope you enjoyed the lecture, and I will see you in the next one.